Alright, welcome back. My friends in Prob&Stats, it's Mr. Who, back at it again for the final lesson of the semester. We're going to talk about simple random sampling. So, this is following off of the last lesson, talking about good and bad sampling. So, we're going to be referencing those notes a little bit, so if you want to have those out too, that'd be great. But hopefully you're ready to take the notes here. You probably have a good idea of what's coming up if you've taken any kind of probability primer in like elementary school or middle school. So, let's get started. Here's our objectives for today. Okay. There's going to be three of them, but we're only going to focus on the first two, really. This third one is, I'm going to talk about it, but I'm not really going to do it. Okay. It takes a little more, on hands. I prefer to be in class with that. So this one's going to be more in class. But the first one is, describe how to obtain a simple random sample. And you can do this either manually or with technology, and we're going to cover both of those, okay, and examples of both. Next is explaining sampling variability and the effect of increased sample size. All right, so we'll talk about that as a second point. And finally, run simulations to test a claim about a population proportion. Like I said, this one we'll be doing more in class rather than here today in the notes. So make sure you kind of stick around in the class for that. Watch out for that. All right, so from last time, I have the definition of random sampling up just in case you don't have your notes out, so you can kind of refresh yourself on what that means. And random sampling is just involving a chance process to determine what members are being sampled out of a population. So hopefully you recall that. Let's move on, okay, to today, where we'll be exploring and defining simple random samples, which, as the title implies, should be fairly simple. All right, so don't think too hard about these topics going forward, okay? But have your notes out and be ready to take some down. First things first, I want to start with a kind of an example first, and a bit of a review from last time. So first of all, we got to ask the question, what is a simple random sample? Like, what am I talking about here? But here's my example, my story to you. If you've ever had any teachers employ the popsicle stick method, which they would use to call on students in class, that was an example of a simple random sample. And remember, when we talk about samples, we have to keep in mind our population and what the sample is. So I'm going to give you a second to describe what the population is and what the sample is, and come back after you try that question and we'll get into it. Alright, welcome back. Hopefully you had some time to think about that using your knowledge of population and sample, but here's what I came up with, is that if you have a teacher who's got a jar for one period of names, then the population would be that one period and students who are there. And then whenever she calls on someone, or he or she, calls on somebody with this popsicle stick, that would be the sample. Students whose popsicle sticks are drawn during that period, which, maybe your teacher samples one or two or three per period. Maybe they sample all of them. Who knows? It depends on how much they use it. But this is an example of a simple random sample. Okay. Here's the definition. A simple random sample, or SRS, I'm not going to be calling it that, but you can always use the abbreviation SRS, of size n is a sample chosen in such a way that every group of n individuals in the population has an equal chance of being selected as the sample. So for example, in my class I have about 22 students, okay? And let's say I use the popsicle stick method, which right now obviously I don't. I'm in quarantine, so I can't necessarily do that. But let's say I had the popsicle stick method, okay, and I draw a popsicle stick out of that bunch of 22 students, then the chance that any person gets drawn is 1 out of 22. And every person has the same chance, equal chance of being selected, where my n is 22, right? So that's what we call a simple random sample. Everybody has the same chance of being selected from the pool of population, and so that's how we do our sampling here. All right. Moving on, I'm going to clear my board. Give me just a sec. But here are some examples of a manual random sample, a physical sample. Okay. I already talked about the popsicle sticks, but if you've ever done this drawing out of a hat thing, that is also a way of randomly sampling. Index cards, kind of similar to that as well. But especially if you're like me, you're a bit of a nerd, and you have played some sort of game that requires dice. Dice is a very consistent probability exercise, very useful tool that is equal on all of its sides. So this is also a good way of sampling stuff manually. Okay. Now, I've shown you all these methods, but they don't always work, okay? There are some times when these methods just won't help us because either our population is too large or, after using them forever and ever, they start to get worn down, and so the size of the things or the use of that object becomes a little worn, and so they're not really perfectly random, okay? In that case, we have some technology options open to us as well. Calculators, like your basic, scientific calculator that you might have, websites like random.org, and even Google. If you search random number generator, it will pop up and you'll be able to use that as your way of picking. Now, it's a little different from just picking stuff out of a hat, because usually that hat is, or the popsicle sticks in this case, are with the name of whatever you're using. But with the random generator, you're going to have to label numbers and attach them to your individuals. Okay, I'm not going to necessarily show that to you here in the notes today because I want to move on, but you can essentially do this. It's kind of like the dice idea, where if you wanted to assign everybody a face, you could use like a 20-sided die to roll from 1 to 20, and then you select the person whose number corresponds with that. So these are options that you might want to explore before class, and if you don't, then you'll probably get to use them during class either way. So, I'm going to spend less time here in the notes and more time in the class talking about these. I use them quite a bit myself, so they are very useful. I definitely recommend exploring those if you have the time. Okay, so next we're going to talk about sampling variability. And I'm going to start again leeching off of 3.2. So last time in 3.2, we learned that sampling bias causes averages for collected sample data to be consistently further away from the true mean. And that's evident right here, where you see the student sample, which was, maybe biased by the students, right? They chose based on what they wanted to choose and not necessarily because they were looking randomly. Some people like long words, some people like short words. Okay, some people like this word over another word, that kind of stuff. So you can see the bias is very, very far away from what the average is, which is marked by this blue line. A random sample is pretty close comparatively, but the true average is represented better, which you would expect. However, it's still not exactly correct. It seems like there's more points on the right side of the mean than there are on the left side. Well, does that mean our random sample is biased? Well, actually, this is a smaller, more accurate consistency, I would say. It is not exact still. Okay, we can never really be exact with a random sample. However, we can account for this little inconsistency, it should say inconsistency, with a thing called sampling variability, a concept we call sampling variability. So what is sampling variability? Well, it is the fact that different random samples of the same size from the same population will produce different estimates. Of course, if I ask you guys a question on one day and sample you guys then, and I ask you guys on another day and sample you guys then, you might not say the same thing depending on what I ask of you. Same thing can be said for, flipping a coin 50 times in a row. If you do that 50 times in a row, you get one result. And if you do it again another 50 times, you'll probably get a different result. That's called sampling variability. Give you a sec to copy this down. Okay, so thinking back, I do want to bring up the last thing from 3.2 again, is this idea of census versus sample. Now, you might not remember census. We didn't talk about it a whole lot, but remember that a census is when you take the whole population's responses and take them as data, whereas a sample is just a portion of the population and it's used to represent the whole. So, recalling this, which of these do you think will give you the most accurate results that reflect the population? Would it be census or sample? Alright, if you chose census, you are absolutely correct. The census measures everybody in the population. Therefore, there isn't really a better way to represent your population than just using the whole population, right? I think that's pretty logical to think about it that way, because at a sample, you're only getting a snapshot of what's, in your population. But with a census, you're getting a good feel for what everybody's responses are like and how they, combine together and make your nice data. Of course, when we talk about census, you can't really, if you're thinking about the U.S. Census, it's not necessarily the same as the census here, but we call it the U.S. Census because it's attempting to collect results from every person in the United States. But as you might know, based on maybe your own personal experiences or you know, just general questions that are being thrown out, that the census doesn't necessarily cover everything. At least the U.S. Census doesn't. You might have missed a couple people here or there, or somebody might be lying. Okay, but aside from those, the census is the most accurate way if you're talking about a population to get data from that population. Alrighty, and that has to do with sampling size. So larger samples of populations tend to reduce sampling variability, with census being the maximum size of a sample you can take. It is the whole thing after all. As more responses are collected, there are less individuals who have not responded, and that's why it's more accurate. You get a bigger picture of how people feel or how people respond to this topic. And of course, to be as accurate as possible, a census is the best choice. Okay, so that is nice to keep in mind. Although, in general, the more samples you collect, the more accurate your data will be. So let's check for understanding here. Let's say I want to collect data on which Pop-Tart flavor is the best between brown sugar cinnamon and frosted strawberry. Those are the two I like the best anyway. So I'm going to use a random sample of my classes, right? And I'm going to sample 7 students out of my class of 24 on day 1. And then on the next day, I'm going to sample 16. So which of these samples is more likely to give me a better idea of which flavor is more popular amongst my students? Give you a second to respond. If you answered the second one with the bigger sample, you are totally correct. Of course, if I sampled the first 7 and they have like a decent split, maybe like a 3 to 4 ratio, and then I'm like, oh, okay, so about half like it or not half like it. Well, remember, that sample is only a small portion of my 24 kids. Right? If I sample 16 and I see a similar result, but it's a little more accurate, let's say it's more like 8-8. Well, that's definitely probably a little closer to home, or maybe it's in a different way, a different skew. Either way, the sample of 16 gives me a better picture of how many people like which flavor better, right? So that's the way that works. That's why large sampling size gives you a better picture of your data. All right, and finally, this is a brief mention. Again, I'm going to talk about this more in the simulations during class. But you might be wondering right now why I even bothered to ask the question twice. Why didn't I just ask everybody in the same time and then just collect the data right then and there? Remember, a sample is supposed to reflect information about the population it represents. Okay, so to use my example here is that I asked on day 1 for a specific sample, and I gave the data for that. But then I wonder if they still think that way. I wonder if their opinion has changed since then. And I ask on another day. That will change some data, but it's basically running the same experiment over again. So what statisticians and researchers do again and again to continue reflecting that information, okay, about the population, is to run the same study or experiment over and over again. Either they do it in reality, which, depending on what you're doing, like mine, is easy to do, or in a simulation, which, if you're talking about something that takes a lot of resources, a lot of time, the simulation does a lot better at that. And again, we'll talk more about simulations during class. Okay, so let's review the objectives here. Describe how to obtain a simple random sample. We talked about what that means, how that works, and what tools we can use to help us do it, either physically or digitally. We talked about sampling variability and the effect of increased sample size, where larger gives you a better picture, gives you more accuracy in identifying what your mean is. Okay. And sampling variability accounts for that small little difference you might see depending on how many times you run the simulation or study of whatever you're studying. And finally, running simulations or running experiments over and over again to test a claim is just to make sure that you're continuing to reflect the ideas you saw from the first time you collected data. And so that's why we do that. Hopefully you found this pretty quick and pretty painless. It is the last lesson of the year. So if you made it this far, congratulations, and I'll see you in class.